Hi, this is a video for CE 505 engineering analysis techniques. And the point of this video is to provide a tutorial for how to solve equations using PTC Mathcad Prime 3.1. And it's also going to give some tips on how to use the plotting capabilities of Mathcad as well. So we'll be defining some functions, creating plots of those functions, and then using solve blocks to solve certain equations regarding those functions. So to get started, let's jump into PTC Mathcad Prime 3.1. So here we go, and I've sort of created this problem in a new Mathcad worksheet, and you can see that it's describing the problem that we want to solve. So in a nutshell, in structural dynamics, there's an item called the dynamic load factor, and it applies for single degree of freedom oscillating systems. And this particular equation is for such a system with some sort of damping mechanism in the system. And also that system is subjected to a harmonic loading, a loading in the form of some amplitude with a certain frequency. It's basically a sine function. But that's just some background. The focus here is on this equation for the dynamic load factor, DLF, that's in terms of this variable xc, looks like a sort of a squiggly line, and then the variable r. So that variable xc is actually the damping ratio, and that's a characteristic of the system that we're trying to analyze. And then r is the frequency ratio, and that's just the ratio of the forcing frequency, so the frequency that the loading is oscillating at divided by the natural frequency of the system that's doing the oscillating or the vibrating. But typically, one or both of xc and r are given in a problem, and we need to either solve for the other one or use both to find the DLF. So there's different things we can do with this equation. So what we're going to do in Mathcad is, let's assume we have an xc value of 0.2. So that's 20% of critical damping. And really the structural dynamics background is not really necessary. What we really want to focus on is this equation and how we can plot this equation and how we can solve it. So we're going to assume that xc is constant at 0.02. So I will just define our variable xc to be 0.20. And then really, that's going to just leave us with needing to define a function for the DLF, and that's going to be a function of that forcing frequency, or sorry, the frequency ratio r. So I'm going to define a function, the DLF, as a function of r is going to be 1 divided by the square root of quantity 2 times xc times r All right, it's acting a little goofy on me. Let's see, times r, and that quantity squared, and then plus quantity 1 minus r squared, that whole quantity squared. So I chose this equation because, as you can see, it's a nonlinear equation, so it's not just a straight line, and it's at least a little bit complicated. All right, and for this xc, since in our problem that's 0.2, why don't we just substitute that straight in there? Right, so here's our equation for the dynamic load factor, the DLF, as a function of r. And what we want to do is find the value of R. In other words, find the frequency ratio that gives the maximum possible value of this dynamic load factor. So what's the R that will give the maximum DLF? And before we jump straight to trying to solve some equations, it can be useful to get a plot of DLF versus R, just to see how that looks. And one of the best ways I found to create plots in Mathcad is to first create what's called a range variable. And it's based on R, so I'll call it R, but I'll call it RS. And how I read that or say that in my mind is it's R's. So I'm defining a bunch of R's that are going to be used to create the plot. So to create a range variable, we do the assignment operator. That's the colon equal sign. And then what we actually have to do is to define the first R value. Let's start at 0 and type a comma. And then we define the second R value, which is really a step value for R. Let's go 0.001. And then we'll define the ending R value and we'll let it go to 2. So what we've defined is the first, the second, which then defines the increment, and then we've defined the last one. And we'll use this range variable RS to create a plot. So let's go to plots and let's insert a plot, an XY plot. And on the Y-axis, it's just going to be our function DLF as a function of the R's that we just defined. And then on the X-axis, it'll be the R's, right? So we get this kind of interesting shape for how the dynamic load factor varies as a function of R. And so what we're looking for is the R value that gives the maximum DLF. And actually, in structural dynamics, when R is equal to 1, that means the forcing frequency equals the natural frequency of the system. That's a situation called resonance. And most people would think that the maximum response, in other words, the dynamic load factor is going to be the greatest at resonance when R is equal to 1. But this plot shows us that that's not actually the case. The R value, the frequency ratio that maximizes the dynamic load factor, is actually a little bit less than 1. And how can we figure out what that is? Well, to get a precise value, we're going to use a solve block. Okay, but what this plot does, it sort of gives us the lay of the land, so to speak. You know, we get a good idea of what kind of function we're dealing with, what it looks like. And then specifically, the plot is going to help us when it comes time to make some guesses. Okay, make some guesses in our solve blocks. So how are we going to find the R value that maximizes the dynamic load factor? Well, we'll want to do the first derivative test. So what we want to do is take this expression for the DLF as a function of R, and we want to take its derivative and set that derivative equal to 0. And whatever R value we get, that critical R value we get when we take the derivative of the DLF and set it equal to 0, that's actually the R that we're looking for. That's the R that will correspond to the maximum possible value of the DLF. So we need to take the derivative of the DLF, and we can do that pretty easily. Well, let's create a variable, and I'll just call it DLF. Right, and the lowercase d, in my mind, that stands for the derivative of the DLF, and this is also going to be a function of R. And we'll assign that to the result of using a derivative operator. We're going to take the derivative with respect to R of our function DLF of R. And if I just let that sit there, that's fine. The expression that's generated when that derivative is taken, it's going to be a really big, long expression. We don't need to look at it to know that Mathcad actually evaluated it and has it stored as this new function, DLF. But if you want to take a peek at it, we can choose our expression and use the symbolic evaluation operator. And this will give us a glimpse of what that derivative looks like. And actually, it's not too bad, right? So maybe I'll just leave it there. This is the derivative with respect to R of our DLF equation, or our DLF function, and this is what we want to set equal to 0. We want to set this equal to 0, solve for the R value that makes this equal to 0, and that's going to be the answer to our problem, and we're going to solve that using a solve block. All right, oh, never mind that siren, that goes off every noon here in the town that I live in, so that's just they're testing our tornado sirens. But so here's the equation. We want to set this expression equal to 0 and solve for R. And that's a perfect job for a solve block. So let's insert a solve block. And there's 3 parts to every solve block. There's the constraints. Now, if we're solving a single equation, the constraints are just that equation that we're trying to solve. We can also use solve blocks to solve more than one equation. If that's the case, we just define multiple equations, and then we can use the solve block to get a solution to several simultaneous equations. But here, the equation we want to solve is this expression, the derivative of the DLF. So I copied that, and I'm going to paste it in our constraint equation. We want this to be equal to 0. And so how do we build an equation in Mathcad? This is very important. We don't use the equivalence operator. We don't use the colon equals sign. What we have to use is the equivalence operator. Or no, we do want to use the equivalence operator. We don't want to use the assignment operator. So the way we get the equivalence operator is to hold down Control and type equals. And you'll see that we get this bold equal sign. That's the equivalence operator in Mathcad, and that's what we use to set up equations. So the equation we want to solve is this, which is just the derivative of that DLF set equal to 0. We want to solve this for R. Now, so that's the first part of the solve block. The second part up here, this is a guess value. We have to give a guess value for the variable that we're solving for. So we're trying to solve for R. So we have to use the assignment operator, that's the colon equals sign, to assign a guess value to R. Now, what's a reasonable guess value for R? Right, we know the R that's going to maximize the DLF is around here. It's about 1, right? So 1 is probably a reasonable guess. You want to try to be in the vicinity of the actual answer if you can. And if you really have no idea what the answer is, if you're not able to get a plot, then I recommend using 1 as a guess. I try to avoid using 0 as a guess because a lot of times, when equations get divided by 0, you get some numerical problems that arise. So 1 is typically a good guess. For this particular problem, 1 is a great guess. So we have a guess assigned using the assignment operator. We have our equation or constraint defined using the equivalence operator, that bold equal sign. And then what we have to do is just invoke the solver that we want to find the value of R. And there's different solvers for different types of equations, different solvers available in Mathcad, but the most basic one, and the one that I always use, is just called find. So use the find command. This is a built-in function in Mathcad, and what we're trying to find is R, and it found an R, and this is maybe another sort of frustrating thing about Mathcad is it finds R, but it won't output the R value unless you tell Mathcad that you want it to. And to get it to output a numerical result, we need to just type the equal sign. Right, so just in the solve block, we see 3 different kinds of equal signs. We see the assignment operator, which is a colon equals. We see the equivalence operator, which is a bold equal sign. And then we see the numerical evaluation operator, which tells Mathcad to numerically evaluate an expression and output a numerical result. And that's what we used here. So we see the answer is 0.959. That's the R value that maximizes our dynamic load factor. So if we want to see what that maximum possible dynamic load factor is, well, we can just take that R value and plug it back in to our function for the dynamic load factor, and we see the maximum value is 2.552, right? So that should correspond to our plot here up front here. This maximum value, 2.552, at a frequency ratio at an R value of not 1, it's actually considerably less than 1. The maximum DLF is at a frequency ratio of about 0.959, right? So I think this is a pretty good example. We practiced defining a function, plotting a function using the concept of a range variable to control really the x-axis, to control the domain for our plot. We used the derivative operator to take the derivative of a function and assign that to be a new function. And then we used the solve block to actually solve the specific equation with a guess value to get an answer. So I hope this helps. If you still have any questions, just let me know. Either shoot me an email or post something in the instructor forum, and I'll be happy to help you. All right, thanks and have a good day.